Those are kind of loud, a little bit of feedback. So, when we left, we were doing a lot of fluoralkylation chemistry. And fluoralkylation, it's certainly important. I'm going to pivot and move on to some other chemistry, and this other chemistry comes from the phase in the group after we had established that the copper chemistry, and after that was already in full speed. Again, there was an interest in exploiting these strategies to access a wide variety of fluorinated substructures, and in early attempts to extrapolate the decarboxylative coupling chemistry to the preparation of fluorinated ketones. We saw how cool those substructures are earlier today. So in an attempt to get the copper chemistry working on to make these types of products, we ultimately were unsuccessful and pivoted to palladium catalyzed coupling reactions. So a segment of the talk, the rest of the talk is going to involve palladium. Fluorinated ketones, I summarized the importance already. This is the exact same slide that you saw 3 or so hours ago. They have unique properties, and they can be used for a wide variety of targets. The proteases are great. You have great conformational control. On the other slide earlier, this was acyclic, and now it's cyclized, and I mentioned that verbally, but now you can see the substructure there. A whole bunch of other targets can be modulated with these types of molecules. As synthetic chemists, we are trained from our first synthesis course that when presented with a fluorinated ketone, we always consider disconnection of the C-alpha C-beta bond. Now, ultimately, there are other bond constructions that you can use, but as a synthetic chemist, that's a retrosynthetic disconnection that should be automatic. So, in the forward reaction, you need some type of a nucleophilic enolate that's intrinsically delta minus at this position to attack an electrophile. We're thinking about simple reactivity right now, SN1, SN2 type processes. I've highlighted the challenges already with this type of bond disconnection. You just didn't realize what I was setting you all up for. Okay. So again, another slide I showed on the conformational control problems, right, the tutorial there. If you attempt to deprotonate this type of a fluoromethyl ketone, when there are other CH bonds available, here we have 2 alpha CH bonds, the non-fluorinated position, using either strong bases or weak bases, the reactions deprotonate at the non-fluorinated position. You do not form the difluorinated enolate that's essential for the bond construction that's shown here. Okay. Now, to solve that problem, there are other strategies. You could make the same enolates using a bromo difluoroenolate, for example, or other halide at this position, using reducing metals, for example, zinc to make a Refermatsky-like reagent. You can generate the appropriate enolates. There's also some retroclason chemistry that's out there that also would do a C-C bond scission reaction to generate the same enolates, and then you can attempt the alkylation chemistry, okay? So deprotonation is tough, but there are some other strategies out there that you can use. The second fundamental problem with this disconnection is that the fluorine atoms decrease the nucleophilicity of the alpha position. They decrease the nucleophilicity through a sigma withdrawing effect, and it's sufficiently decreased such that simple electrophiles preferably react at the oxygen, not at the carbon. So you get this methyl ether as opposed to making the new C-C bond here at the alpha position. Okay? So again, another fluorine effect perturbing the reactivity. It's perturbing the deprotonation, and it's perturbing the C-C bond forming reaction that we want to happen. There are some recent solutions to this challenge, this problem. An older solution would involve the use of superstoichiometric zinc. A newer solution after, 5 years after we were in this space, involves the use of HFIP as a unique solvent. We've seen HFIP in some other cases the last couple of days be a really important, yesterday actually, right? A really important solvent for promoting some of the asymmetric transformations, the phosphine catalyzed reactions. So anyways, you can use some additives. You can make the C-C bond that you want there. That's great. That wasn't available at the time. We resorted to a different strategy in which we need to set up our substrates a certain way. So in this case, we'll take our electrophile and attach it to the nucleophile using CO2 as the linker. And with this strategy of palladium catalyzed oxidative addition to the benzylic position and subsequent loss of CO2 places the palladium at the appropriate fluorinated position. There's no isomerization over to the non-fluorinated position. So it's a decarboxylated strategy for generating the appropriate enolate, and then from this enolate, palladium-2 to palladium-0 reductive elimination would generate the C-C bond. Okay. So that's how we solve those two issues, those two problems using a palladium-based catalyst system. The system itself works for a variety of ketones. You can see heterocycles are tolerated on either the benzylic moiety or over on the other side the ketone. Electron-rich and deficient substructures work. These are done at 120 degrees. We require 140 degrees for this reaction because you have this alkyl tail. The alkyls are a little bit more difficult to work with, and you need a higher temperature for that. The strategy also works for the preparation of allylic substructures, and so the key disconnection is shown here. We can break the C-alpha, C-beta bond. When we break that, we have a difluorinated enolate. And this one is showing the anionic charge on the carbon as opposed to oxygen, but you have the different resonance forms of that hopefully is easy enough to see. And we would have an allyl cation. We link those two species with CO2 when we're preparing the substrates. In a long history of palladium catalyzed cross-coupling reactions, allylation reactions of hard nucleophiles, ketone enolates are hard nucleophiles, there's a wealth of literature indicating that hard nucleophiles preferentially react at the terminal position to make these linear products. Hard nucleophiles rarely will attack at the internal position to make these branched products. Okay? There are a couple of rare cases. One of that was available when we started the project. This one came out kind of after we had our first publication in this area. Okay. But with palladium catalyzed systems, hard nucleophiles react over there. It turns out that fluorine perturbs the reactivity, so we can access either the linear or the branch products as a function of the ligand we use for the system. So if we have different phosphine-based ligands, you can select one product over the other. A series of ligands is shown here, demonstrating the structure-function relationships of the ligands. If you have a bulky biaryl monophosphine, here's the T-butyl group, you predominantly form the linear product and good selectivity. As the phosphine becomes less bulky, the selectivity flips. And if you make it electron deficient and smaller, you get even better selectivity. Okay, so the substituent of the phosphine regulates the selectivity of this transformation. I'll explain why, or a working model, in just a couple of slides. The reaction works for a variety of substructures shown here. Again, T-butyl Brett-phos generates the linear product, phenyl X-phos generates the branch product. In the case of the branch product, the selectivities are excellent, regardless of the substituents on the ring. So you have electron-deficient substrates, electron-rich substrates, awesome selectivity. Most cases are greater than 49:1. However, the selectivity varies as a function of the groups on there for the linear cases with T-butyl Brett-phos, and I'll explain why that's important in just a couple of slides. Okay. The ability to access the branch product is dependent on the fluorination state of the substrate. So in this series, I'll just show two reactions for the difluorinated, monofluorinated, and non-fluorinated substrates. And we're going to look at the two catalyst systems, the catalyst system that predominantly forms the linear product and the catalyst system that forms the branch product there. All systems can produce the linear product. That's the product that's typically easier to produce with palladium-based catalyst systems and hard enolate nucleophiles. Excellent selectivity with the difluorinated, the non-fluorinated, and the monofluorinated. This reaction itself with the monofluorinated had been optimized by others, so we spent no time trying to improve this reaction. There are other systems that can do this just fine. Palladium can do that. In contrast, only the difluorinated substrate can access the branch product. And you can see the optimized conditions there, excellent yield, excellent selectivity. If you remove one or both fluorine atoms, the selectivity immediately drops off. So somehow the presence of fluorine is enabling the access to that branch product. And again, I'll explain the model in just a couple of slides. Our working hypothesis involves a mechanism by which a palladium pi-allyl species is a key intermediate for both steps. In order to probe that hypothesis, subjection of either the linear or the branched substrates to either set of conditions generates product that's either linear or branched as a function of the ligand. So we can take this substrate, generate the pi-allyl intermediate, and the ligand controls the selectivity, and that works both ways. So the ligand is controlling the selectivity. There's no memory effect, there's no template effect. We're likely going through a pi-allyl based on this experiment. Now the working hypothesis, there are three different working steps in this hypothesis, three different paths in this working hypothesis. In the first path, dissociation of the enolate from the metal and subsequent attack through an outer sphere process could undergo two different bond connections. The enolate could attack the terminal position to generate the linear product. It could attack the internal position to generate the branch product. Those would be in competition with each other, and we think that's a competition that's relevant for one of the catalyst systems. However, another CC bond forming event might involve slippage of both the enolate and the allyl group to these eta-1 coordination mode, in which the palladium templates the allylic fragment and the enolate fragment. In a pericyclic-like transition state, a palladium 2 to palladium 0 reductive elimination could presumably form the CC bond, the carbonyl, and present the allyl group in the alkene in the correct position. Now, this transition state might be dominated by the fluorine atoms that are increasing the electrophilicity of this system. So, hypothetically, our proposed model involves the attack of the pi-allyl in a nucleophilic sense to an electrophilic difluorinated position. Okay. This type of perturbation is known if you go back to classical Claisen reactions that proceed through a six-membered ring transition state. The reaction of the non-fluorinated enol ether here occurs under high temperature and good yields. The transition state would look something like this. You would have a nucleophilic enol attacking the allyl substructure to make that branch type product. The introduction of fluorine enables the reaction to occur in quantitative yield under much more mild conditions. The transition state in that case, again, in my mind, the way I think about it, you have the inductive effect of the fluorine atoms increasing the electrophilicity at this position. So it's kind of an Oompa-Long strategy. Instead of being nucleophilic at this position, now we're electrophilic at this position, and we encourage the attack of the allyl system. If you compare this transition state to this one here, they look very similar. We've just inserted palladium right there in between the carbon and the oxygen. So that's an analogy. It's a working model. It's a hypothesis. Maybe there's some experimental evidence and rationalization that I can provide to further substantiate that working hypothesis. So the first evidence I'll show you that helps support these two working processes. Again, in the case of one catalyst system, we have dissociation, and then these two paths that can both occur. In the other catalyst system, we have this over here. Okay. We'll use a linear free energy relationship to look at the selectivity of branched versus linear products that are formed in this reaction. Okay, so here's the series of substrates shown there, from electron-rich to deficient species. Our parent substructure with just a phenyl ring here is going to be the 0 point for this LFER. The data shown here, I don't always show the data, but since I have a little bit more time, trying to take up 2 hours, I'll throw in an extra slide here and there. I've done that along the way, and here's another one. You just don't know which ones they are. The linear free energy relationship shows an amazing correlation. Electron deficient substrates give higher selectivity for the linear product. The electron rich substrates give you product in lower selectivity. The correlation is excellent. The coefficient here of 0.45 is indicative of a cationic transition state. The comparison there also is with sigma plus. Okay, so it's evidence of a cationic intermediate. And certainly this species here is cationic, right? It's a pi allyl. There's a cation here. We rationalize the selectivity here as a buildup of a positive charge, and then the more reactive substrates that have electron deficient groups will react kinetically faster through more of like an SN2 type process. There's more of an SN1 like stabilization when you have donating groups here, and that rationalization has been supported by used by others before us. So we definitely rely on some giants in the field for this analysis. In contrast, the other process that's dominated by the 2 fluorine atoms here perturbing the reactivity, that process shows no LFER. The selectivity is excellent, it's exquisite, it's exclusive, regardless of the functional groups on this ring system. And again, we think of that as a system by which the fluorine is perturbing the reactivity, making an electrophilic center, and then the pi allyl system, which is cross-conjugated with the phenyl ring, is attacking there. So the electronic character of this R1 group really doesn't influence anywhere near as much as what's going on around this ring system in the pericyclic transition state. It's hand-waving, and it's an explanation. It's our current working model. Okay. Based on this model, we can now rationalize why the ligands provide the selectivities or give the different regioisomers. So let's walk through that rationale quickly. The bulky electron-rich ligand, if it's bulky and electron-rich, it can more easily push off an X-type ligand, in this case the enolate. The enolate requires dissociation for this outer sphere attack, so maybe it's the steric bulk and the fact that you have more stabilization from the ligand. Maybe that's the important part for this pathway. It's a bulky ligand. In contrast, a smaller electron deficient ligand would facilitate a process for which you need the enolate to stay retained on the metal in the transition state. And so again, as you go smaller, as you go more electron deficient, you promote this process selectively. And again, we think that it supports this working mechanism here. Okay. Again, that's our working model. It might be right, it might be wrong, but we kind of left this project and moved on to other things. I'm going to cycle back and just remind you of the first sub-story I told in this sequence. It was about the benzylic substrates, and the benzylic substrates, again, are activated and prepared in such a way that the activated benzylic position after decarboxylation and CC bond formation generates these products. You can see the blue bond connecting the C alpha position to the position where our electrophile was placed. While Ming Xu was optimizing this reaction, there was an annoying side product that would show up every once in a while, 3% yield, 5% yield. Wanted to get rid of it, wanted to have nothing to do with it. At one point, she ended up characterizing it and figuring out what was going on there. And it was a surprising product that was forming in small quantities. It was a product in which the enolate nucleophile had connected over to the para position. So this is a net paraselective CH functionalization, but it's from a benzylic substrate. Okay, so it's an unusual reactivity. You can see the red CC bond that's formed there. But presumably the hydrogen that was over here might have migrated over there and made the third hydrogen in the methyl group. Ultimately, that was further optimized. She learned how to selectively form that compound. There were several different systems that seemed to promote this reaction. One we never published was with an electron-rich phosphine ligand. You can see some of that data buried in the SI, but notably the presence of a base, an appropriate base, facilitated the paraselective C bond forming reaction there. And so I'm going to show you data in just a little bit in terms of like how the base regulates the selectivity and how important the base is for the selectivity. Do note that the conditions are the exact same catalyst, same solvent, same temperature. There's nothing different other than triethylamine in those reactions. There's no other tricks going on. The reaction itself works for enough, a variety of substructures here, electron-rich and deficient. Substructures are tolerated. You can tolerate substituents at the ortho or meta position of the arene. You do not tolerate substituents at the para position. We actually need that position unblocked so we can form a new bond there. Okay. Heterocycles are tolerated. You can have electron-rich and deficient groups over here on the ketone enolate moiety. Now, there are some important properties of the base that modulate the selectivity. Note this chart is selectivity. This is not yield. This is selectivity on this axis here. We're looking at selectivity for arylation versus benzylation. Arylation would be high selectivity, benzylation would be down here low. So, reaction that gives 0 could still be 99% yield. The selectivity factor we're looking at. We're looking at that selectivity as a function of the pKa. Okay, so if you have an amine with sufficient basicity and it's reasonably small, you get high selectivity. Selection of bases here, you see trialkyl amines, TMEDA, DMAP works sufficiently for this transformation. If the amine gets too big, too bulky, you lose selectivity, you selectively form the benzyl product. So you can see triethylamine relative to tripropylamine, we've lost substantial amount of selectivity. Hoenig's base, terrible. Gives you all the benzyl product over here. The pKa of the base is important. That's a key player. And so if you strip down DMAP into the aniline and the pyridine moieties, you can quickly see that if the amine is insufficiently basic, you lose selectivity. Those provide the benzyl product in high yield. Okay, but the pKa of the amine is important. The steric hindrance of the base is important here. The concentration of the base is also important. So this data correlates the equivalence of triethylamine with the rate of the reaction. You can see an increase in rate of the reaction as we sequentially add triethylamine. The maximum is about 1 equivalent there. The rate of the reaction also correlates with the selectivity. So in this three-way correlation, the ratio of arylation to benzylation increases sequentially up to 1 equivalent. You get really not much benefit after you go past 1 equivalent there. Okay, so the concentration of amine influences the rate and the selectivity. Amine is really controlling this reactivity. A working mechanism is shown here. I'll try to substantiate it with some experimental evidence in the next series of slides, but first let me introduce you to what we hypothesize is going on here. From a palladium 0 base catalyst system, an oxidative addition would make a pi benzyl species. The resulting carboxylate anion is a weakly coordinating anion, and so that can dissociate from the metal, decarboxylate, and then reassociate. And when it's decarboxylated, you're going to have a tighter affinity between the metal and the X-type ligand. Now, the enolate can coordinate by either the O or C base coordination modes, and computational evidence I'll show in just a little bit suggests that those are in equilibrium, 1-to-1 ratio. From the C-bound enolate, a classical CC reductive elimination would generate the benzylation product and regenerate your palladium 0. But from the O-bound enolate, perhaps the geometry between the 4 position of the pi benzyl species and the alpha position of the enolate allow for CC bond formation between those two moieties. And through a pericyclic-like transition state, a reductive elimination that takes your palladium 2 down to palladium 0 and generates a CC bond would also present an acidic methine proton. It's acidic because you have two allyl groups attached to it. You also have a fluoroalkyl group. You expect each one of those to sequentially acidify that position. With an acidic position, a basic amine might deprotonate this position, allow aromatization, and transfer the proton over there to the benzylic position in an inner sphere process. So that's the role of the amine additive in this working model. You deprotonate, you reprotonate, you generate the aerylation product, and then you regenerate palladium 0. That's the working model. I'll show you an array of experimental data that supports this and or refutes some other models. Initially, I'm going to demonstrate data suggesting that you have free association here, solvent separation of the carboxylate anion from the palladium. So a straightforward experiment here would be a classical crossover experiment. You have a labeled substrate, you have the methyl and isopropyl, and then H and methoxy. If you have crossover, you would expect a 1-to-1 to 1-to-1 to 1 ratio of 4 products, and with experimental error, we get that. Okay? 15, 15, 15, 13. That's statistically what you would expect with an error of the measurement. So we get crossover. We think it's early stage crossover. Another classical experiment, if you aim to probe for metal hydride or metal aryl intermediates, is to run the reaction in the presence of a deuterated solvent. If you have a discrete metal hydride or metal aryl intermediate, you would see introduction of the deuterium onto the aromatic ring. The reactions, when run in methanol, do not produce any deuteration of the aryl ring. The reactions form the anticipated product in addition to some material that's deuterated at the alpha position. And so that's evidence of an enolate that can dissociate from the palladium, or is dissociated after the decarboxylation, okay? So we deuterate this position, we have anionic character there. We don't seem to have palladium metal or palladium hydride or palladium aryl intermediates. Discrete evidence for the transfer of the proton from the para position to the benzyl position was established using a simple deuterium labeling experiment. You can see the transfer of the deuterium over to the benzylic position is excellent. Now, the transfer of the deuterium occurs after the rate-limiting C-C bond forming event. Okay? You make the C-C bond, and then the deuterium transfer happens. In order to probe that, we had to invent a new type of substrate, a tri-labeled substrate. I haven't seen this type of experiment before. In this substrate, we have a label here on the ketone moiety, a label there on the benzylic moiety, but we also have a third label over here on the benzyl moiety. 3 labels, 2 by 2 by 2, possibly 8 different products if we have full scrambling of everything. But we're only going to see 4 products in this reaction. This reaction specifically probes whether transfer of the deuterium happens after C-C bond formation. If transfer of deuterium happens with an inner sphere process after C-C bond formation, the deuterium will stay attached to all the products that contain isopropyl. If it's an inner sphere process, the deuterium should not cross over to the other substrate. So that's what we're trying to probe here. In fact, that's true. I'm walking through it because, yeah, it's going to be true, right? Okay, so we see 4 products. The 4 products have the labels as shown. Most importantly, I bolded the deuterium stays attached to the moiety bearing the isopropyl group. In all of the products we see, the hydrogen stays attached to the methyl. So the deprotonation, reprotonation occurs within the solvent sphere at the end after you have scrambling, after the C-C bond formation. Computational evidence was further substantiated by Paul Chung's group, great collaborators. Initially, I'll rule out any suggestion that there's a thermodynamic process controlling the selectivity. Computationally, the aerylation and the benzylation products are equoenergetic. There's no thermodynamic control in this system. I already suggested that the C-bound and O-bound enolates are equoenergetic, and within computational error, you can see that's true. So those should be existing in free equilibrium, back, forth. The CC reductive elimination to make the benzyl product involves a transition state. That's 27.7 kcal per mole in energy there. That transition state involves dissociation of a phosphine ligand to make a less stabilized palladium intermediate, then slippage of the pi-benzyl moiety to an A-to 2 coordination mode is required for forming the CC bond there. That's a unique transition state. We weren't expecting that. But ultimately, that generates the benzylation product. Now, when thinking about the mechanism, that pericyclic rearrangement type process to generate the aerylation product, let's look at the energy trajectory for that. So the transition state for that pericyclic intermediate is lower in energy, 23.5 kcal per mole. That's actually lower than the transition state over here. And the intermediate that's de-aromatized but still coordinated to the palladium is actually pretty reasonably placed. 11.5 kcal per mole there. So in these reactions that are forming benzylic products, these computations suggest that you have an equilibrium here, you have a lower energy pathway actually going over here, but with no opportunity to do anything. Microscopic reversibility, you do the retro 3-3, you come back through this energy landscape, go back to the enolates. Ultimately, you're going to keep going back and forth until you get to the benzylation product. That's what these calculations are showing. Okay. Now, in the presence of an escape route, perhaps we can trap out this intermediate. That escape route is enabled by the amine base. I already showed you how important that amine base is for controlling the selectivity. So here's our activated methine, deprotonation of the activated methine by trimethylamine. This is a model for triethylamine. So in the model system, the deprotonation has an energy, a transition state energy of 26.5 kcal per mole. That's lower than the transition state over here for benzylation. So you have the right amine, a small amine, a sufficiently basic amine, the energy associated with deprotonation here, and presumably the subsequent step of reprotonation of the benzylic position there's a low energy pathway there. You form the aerylation product. If the amine is insufficiently basic, the computed energy level is too high. So pyridine doesn't work. Pyridine doesn't give you this product, and the computations support that. Here we're at 32 kcal per mole, certainly higher than your 20.7.7 over there. Okay, so these suggest these support the working model. It's the model that we're going with right now. Reviewers weren't happy enough. They thought it was a fluorine trick. They said if you can only make fluorinated ketones, that's not enough. That's not impactful enough. So in response, I'll show you a couple of examples here in which we can flip the selectivity of other reactions that are not fluorinated using the same trick. The trick is an amine trick. This is a reaction from a former colleague, John Tunge. His office is right around the corner from mine. He had this nice publication shortly after I joined KU. It was a palladium catalyzed coupling reaction. Again, oxidative addition, decarboxylation, and you couple the alpha position of a nitrile to the benzylic position. Really nice reaction occurs in over 90% yield. Taking his same reaction conditions and presenting those conditions with a base flipped the selectivity. So instead of a CC bond forming reaction at the benzylic position, now you get a paraselective CH bond formation just with the amine base. The selectivity isn't perfect. You can further optimize the condition, change the catalyst system, change the amine, and we get excellent selectivity, synthetically useful yields of the paraselective product. The amine base, in this case the T-butyl TMG, is really driving the selectivity here. In a mechanistic analysis, if you do that, you'll perhaps draw something like this. You still have your pi-benzyl coordinated to the nitrogen of the nitrile. The nitrogen can then form a bond from the alpha position to the C4 position. A pericyclic-like transition state in the reductive elimination process would generate an activated methine proton. Again, deprotonation, reprotonation over here would aromatize the system. Okay, you need a little bit of a stronger base there to get this one to go because you don't have the fluorinated groups further acidifying this position. Nonetheless, we're still controlling selectivity with the base. Okay, so what's next? Maybe we can exploit this strategy to take on other challenges, and one challenge might be CH functionalization of feedstock chemicals. Certainly we like to take oil reformats and make value-added compounds using simple systems, direct systems. Let me show you one thought on how you might take toluene and do a para-selective functionalization of that molecule. It's a challenging reaction because the weakest CH bond is actually going to be the benzoylic position, so that's going to be easy to functionalize, but how would you functionalize this over here? An additional challenge is the regioselectivity, so if you try to functionalize the para position over the meta or ortho positions, the statistics are against you, right? You have 4 other positions, we want to do this one position. We want to get this position, we don't want to touch the other CH bonds. So you have regiochemistry issues, you have chemoselectivity issues. Let me suggest one opportunity to do this transformation, one process that might be used to selectively functionalize the para position of toluene. Specifically, the strategy will involve functionalization of the weak CH bond and then transfer that functionality over to the para position. So in an early synthetic sequence, a radical classical bromination of toluene generates benzyl bromide. We get rid of excess HBr just by bubbling through N2. We do send that gas through traps. Don't just push HBr out into the atmosphere, push it through hydroxide traps properly. From there, in the same pot, you throw in the pronucleophile, platinum-based catalyst system, a combination of bases, and you get the para-substituted product in a single yield from toluene. Now that product itself might not look the most interesting, might not be the most useful, but perhaps with some synthetic creativity, some further functionalization, halogenation, classical, just SN2 heterocycle alkylation chemistry, you might make compounds of increasing complexity and some of which are at the complexity of FDA-approved therapeutics. So there's lots of things you can do. You can functionalize the nitrile, you can functionalize over here. Perhaps your pronucleophile has different moieties over here, different groups there. Perhaps we can get to other interesting substructures with this type of strategy from toluene. So, that there is basically where I am ending the day. I've taken you through quite a few different transformations. Hopefully you've seen the evolution of a project and a proposal into a program. So some of you individuals who are thinking about being a faculty member someday, many of us get really focused on projects, but if you get that first reaction to work, the second reaction to work, how do you see 10 reactions, or how do you see a career develop, even after you get that first one? So be thinking about that also. What's the difference between a project that a student might be working on in a program? Okay. Hopefully, there's been some learnings on the synthetic part that complements some of the things we've been talking about on the med chem side. Hopefully the appreciation of the physical organic chemistry and the physical chemical perturbations imparted by fluorine was apparent here. I hope also it was apparent on the other part of the course. And if it wasn't, I really haven't done my job. So other than that, I'm very appreciative of group members. I've highlighted individual ones throughout the slides who contributed to the projects that I demonstrated, the projects that I showed. The work here had been supported by a series of young faculty grants that ultimately, were, and also larger grants from the NIH. So grateful for all the funding we've had, but the ones that supported the project shown here are highlighted there. Other than that, it's been a fun week, a week in which I'm losing my voice right in front of you guys, so I'm going to be quiet there. Thank you all, and it's been a fun interaction, and I hope that this inspires you to do great things in your futures. All right? So thank you.
So I think we can take a couple of questions. Any questions? So I don't
this alkylating ketones.
Yeah. So phenyl is on a geminal position. If that phenyl is in medicinal position, what kind of reactivity will you have?
So it was this reaction here that you're asking about?
Yes.
And specifically, you're asking if I have a phenyl group where?
Medicinal position.
Sorry?
Medicinal.
Medicinal. So if it's over here?
Yeah.
So those substrates did not work well. I'm going to maybe go back a couple of slides here and see if I can find it. So you're saying if I had this and I had a substrate here with a phenyl group here? So I have two different comments there. If you want, I think that's this substrate down here.
That phenyl is again next position on that part.
You want it here?
Here.
Yeah, we didn't explore that one. I don't know mechanistically in my working, the model in my head and that I showed you. I think it should work okay for either system. Note that that's if you do not have this one and you just have the phenyl ring there, then you don't have the issue of linear branched. So either make a CC bond on either side is chemically equivalent. Okay, I think it would work, but I don't have experimental data to support that. The pericyclic transformation would similarly work just fine in the working model.
And that is only one product is formed. If you use any kind of ligand.
If I use any kind of what?
Yeah.
Yeah, sure. And it's definitely true in cross-coupling chemistry in general. Sometimes you make like subtle changes to your substrate and then you just need a different ligand. That's why there are so many phos ligands out there, right? Is just minor changes to the substrates require modification there. Okay.
In the last mechanistic you have done the
You have to talk a little bit louder because that's kind of loud too. So in the Nature Chem paper, what?
Sir, in the last mechanistic you have done the
Yeah. Which mechanistic part of this, or which study? This is that one.
Last one, we go back to the scientific.
You want the computational part? So communication. Sorry, I thought it was saying Nature Chem.
The last one.
The last work? What do you want to see though? Like the mechanism? So I guess what's the question? This is the mechanism. So what's the question?
The same.
What's the question? All the reaction was done with the light flow and the last, as you told us, like reverse addition reverse. So you have not defined the side effect performance.
Right. So what that was the question?
If the same side group we have and light flow.
Difluorocyano. Okay. Yeah, so the question, did you do it with difluorocyano? No, we were struggling to prepare that substrate. There are other challenges that you should be aware of and thoughtful when you're preparing substrates. So one substrate that we had worked with a little bit was a substrate for which if you replace one of those methyl groups with a fluoro, you make the fluoromethyl product. It turns out when you subject that to base, you competitively eliminate. So if you have a fluoro here, then you have a vicinal hydrogen and you can eliminate and make an alkene. So you can get some of the product, but you also get some elimination. And we can't completely solve it, just like optimization. I think process groups with high throughput experimentation, Bayesian optimization strategies, I think you can solve that now. But at the time, it was really tough and tricky. You get 20 or 30% yield of some of these other derivatives, but again, just never really solved it well enough.
And sir, one more question. The first slide where you have shown that crystal group, if we remove crystal group with the activated crystal like N-hydrox, N-ketimine, trifluorilation,
I think I know which one. Yeah, where you're making the new reagent. So that would be back up here in this section.
Yes.
Yep. So what about it?
You know what actually you told that remove the like leaving some byproduct was coming like methanol
Mhm.
decreases. So instead of that, if we have activated ester like and element.
Sure.
So
So, right. So, I think that would look something like that with an NO on it. This is a subset of things we probably tried 3 times this many. I don't know for sure that we tried the N-hydroxythalamide, but I speculate that we did try it. This is just kind of what fit on the slide and what I use for presentation purposes. The SI has some more examples. So, okay. Certainly there are other things that can do transesterification reactions. Perhaps there are other solutions for this problem.
Okay, I think so. With no more questions, now I think we take a break because we need to quickly come back for the lecture section for this GAN course. So we just thank Dr. Arpan again. Let's take a quick 10 minutes break. We have a tea, and after tea, those who expert on the GAN course should again gather back for the director function. We have Dr. Arpan